We are on Unit 4, Intramolecular Forces. Here is an overview. There are three major topics: covalent bonds, ionic bonds, and metallic bonds. And there are 9 topics for covalent bonds, which will be the subject of this lesson. And there are 5 topics for ionic bonds and 2 topics for metallic bonds, which we will learn later. So let's look at the overview of intramolecular bonds. This is found in chapter 7 and 8 in your textbook. There are 2 kinds of attractive forces that operate in a molecule or a compound. They are intramolecular and intermolecular forces. Intra means inside, inter means between. So the bonds between atoms inside a molecule or a chemical compound is intramolecular bonds, and that would be covalent, ionic, and metallic bonds. Covalent bonds share electrons. Ionic bonds are formed by 2 atoms exchanging electrons. Metallic bonds are formed by metal atoms sharing valence electrons as a sea around them. So intermolecular bonds are attractions between different molecules, as the 3 shown below. And I am going to give you some examples. Here is an example of an intramolecular bond. The hydrogen and oxygen atoms of a water molecule are connected by these atoms. But if you look at these 2 water molecules, they are interacting with each other because of electrostatic attractions between the small polarity of hydrogen and the negative polarity of oxygen. This is called an intermolecular bond because it's occurring between the molecules. These are important for keeping things mixed together, and this forms substances. We will look at intermolecular bonds in Unit 7, and we will look at intramolecular bonds in Unit 4. Introduction to covalent bonds. I will give you 9 bullet points and brief descriptions so that when we cover each one in detail, you won't be confused. First thing, covalent bonds are electrostatic attractions formed by 2 different or same nonmetal. They share their valence electrons between them so that they can obtain the nearest noble gas electron configuration and be stable. So if you look at the fluorine in this example, it's a group 7A element. It has 7 valence electrons. To fulfill the octet rule and have a stable set of valence electrons, it needs 1 more to become 8. So 2 fluorine atoms can say, hey, I can hang out with you, and combine together to form a Lewis dot structure of a F2 or fluorine gas molecule. And this is the covalent bond. This is 1 pair of shared electrons. So when chemicals form covalent bonds such as this, they can be either polar covalent or non-polar covalent based on the electronegativity difference of the 2 atoms forming it. In this case, because you are the same element, the electronegativity would be 1 value minus itself, which will be 0. This would be a non-polar example. If you are bonded with a very electronegative and a not very electronegative atom, then you will have a large electronegativity difference, resulting in you becoming a polar covalent bond. All molecules are made out of covalent bonds. All gases, except noble gases, and ionic substances like sugars, lipids, proteins, and nucleic acids are all made out of covalent compounds. So essentially, you are made out of covalent bonds. And you must be able to draw covalent molecules using Lewis dot structures. We will look at that in a later lesson. The shared electrons shown over here, they don't fall into the normal orbitals. They are in a special hybrid orbital slightly outside of the original one that is accessible to both atoms. And here's a look at the 4 types of macromolecules, all stitched together by covalent bonds. And going back, so covalent bonds can be single, like this example, double if you share 2 pairs, and triple if you share 3 pairs, based on the number of electron pairs shared. Bond length, the distance between the nucleus of one atom to the nucleus of another atom in a bond. This decreases when more electron pairs are shared. The lowest would be bond length is highest in single bonds, second highest in double bonds, and lowest in triple bonds. Bond dissociation energy, like breaking up energy. So when you break up next time, you can say you dissociated with that person. The dissociation energy increases with the number of electron pairs shared. It makes sense. If you have a triple bond, it's 3 times more difficult to break, right? And also, it's much easier to break a single bond. The energy required to create a bond is equal to the dissociation energy because it's the same energy that goes into both. And also, if you have a large electronegativity difference, the dissociation energy is high. And then, based on the electron pair repulsion of bonding atoms, bonding electrons, there are 3-dimensional shapes and bond angles formed. We will discuss that also. This leads to different molecular geometries. Finally, we will look at naming binary compounds made with 2 different elements. And how you name them based on how many atoms of each element is present using prefixes. So, first topic is calculating the electronegativity difference between atoms. We could not do any of that without the research of Dr. Linus Pauling, who received a Nobel Prize in Chemistry in 1954. For his discovery of the electronegativity values of different elements and how electronegativity difference impacts the type of covalent bonds formed and how intermolecular bonds are impacted with electronegativity. He is also the only person to receive 2 unshared Nobel Prizes. He won another one in 1962 for his work on opposing the weapons of mass destruction, nuclear weapons, and so forth. So let's take Dr. Pauling's electronegativity periodic table chart. Note that noble gases are not electronegative because they don't participate in electron sharing. And fluorine is the most electronegative, and drawing a diagonal leads you to the least electronegative cesium. It's 0.7 and this is 4.0. So I need you to memorize this, that anytime you have 2 elements whose electronegativity difference, absolute value of it, is anywhere from 0 to 0.4, then you form a non-polar covalent bond. And then you form a polar covalent bond when your electronegativity difference falls between 0.5 and 2. And if you are a metal interacting with a non-metal and you have electronegativity difference between 2.1 and 4, you are a ionic bond. So you're going to first calculate the electronegativity difference and then find where in this diagram the difference fits to find the type of bond. So let's look at a problem. Lithium oxide, LiO, is an ionic, is it ionic, polar, or non-polar based on its electronegativity? First, you have to forget about how many subscripts there are showing how many atoms are there. Just need the types of atoms. So lithium, if you look here, it's 1.0. and oxygen is 3.5. So the absolute value of this is going to be highest number minus lowest number, which is 2.5. 2.5 fits over here, meaning that it is an ionic bond. So this is an ionic compound. Another way to treat on this, look, it's lithium and oxygen. Oxygen is a nonmetal, lithium is a metal. So this has to be a ionic compound. And pause this and see if you can answer these questions. Calculate the electronegativity difference of these compounds and determine which ones are ionic and find their whether they are polar or non-polar. So if I ever give you just a molecular formula, you are going to just say hydrogen and hydrogen, magnesium and oxygen, carbon and oxygen, and so on, and calculate the difference. Pause and see if you can do it. Okay, so these guys are made with magnesium, lithium, and potassium, which are metals. So these three are going to be ionic compounds. And then you can calculate the electronegativity difference. If you are made out of the same element, then you're going to be 0. And if you are made with two electronegative elements that are not too high in electronegativity, you're going to be polar. And if you have a very high electronegativity, you're going to be an ionic compound. Okay, topic 2. Covalent bonds are formed between nonmetals. So if I give you a set of elements and molecules, their chemical formula, and I ask which of the following are covalent bonds, or I say they're not covalent compounds, how would you answer that? You're going to look at this. You need to remember this. I showed you this in the periodic table notes. And if there is a metal shown in blue anywhere here, it's not going to be covalent. Anything else will be covalent. So here are the metals, and these guys are ionic compounds. Everybody else is a covalent compound. Topic 2. Topic 3. The types and the lengths of the covalent bonds are based on the number of electron pairs shared. So let's look at 3 different compounds: HCl, which is stomach acid, carbon dioxide gas, CO2, and nitrogen gas, which is the most abundant gas, 80%, I believe, in the atmosphere. So first you're going to draw each one like this. Hydrogen has 1 electron shown in green. Chlorine has 7 shown in gray. They need to combine with each other to gain the 1 electron chlorine is missing to make an octet. And hydrogen needs 1 more electron to look like helium. And then they're both happy. And this electron pair is shown as a single line or a single bond. That is a single bond shown by the arrow. If you are making CO2, since there is 1 carbon sharing electrons with 2 oxygens, you're going to put the oxygens on either side like this. Oxygen has 6 electrons shown in black on either side, and carbon has 4. You're going to align 2 and 2. Carbon needs 4 more, right? So you're going to take 2 electrons from this guy and 2 electrons from this guy, and then you have your 8. And oxygen in turn needs to share 2 electrons with each carbon. And then you get 1 and 2 double bonds on this each side. Nitrogen, a group 5 element, has 5 electrons and needs 3 electrons. So if nitrogen hangs out with nitrogen, they both need to share 3 electrons with the other one. So this pair, and this pair are shown as 3 lines here. So going from this direction to this direction, the bond strength increases and the bond length decreases. Topic 4. Types of covalent bonds based on electronegativity difference. We already discussed this, so I'm going to breeze through this. If you have a difference between 0.5 and 2, you are going to be polar covalent bonds. one of the atoms is going to be extremely electronegative compared to the other one, and will have a partial positive charge shown over here. This is the electropositive one, and this is the electronegative one. The electronegative one will pull the shared electrons towards it, giving it a tiny positive charge. I mean a negative charge. And the other one gets a tiny positive charge. This causes the creation of a dipole or a two opposite poles, because of the unequal electron sharing. And here's a Lewis dot structure of the water molecule. And now let's look at nonpolar covalent bonds. They are formed by two atoms with equal electronegativity and a small difference between 0 and 0.4 in the Pauling scale. If you look at these two atoms, fluorine and fluorine, you can draw them like this, because the electronegativity is the same for both and their difference is 0. And these electrons are equally shared. Here, the electrons are not equally shared. Number 5, how do you draw Lewis dot structures for formulas with covalent bonds? So first you have a molecular formula. It shows the number of each type of atom and the type. Then you have the structural formula drawn with the lines and the chemical element symbols. It shows how they are connected in two-dimensional space. And then the Lewis dot structure shows how individual electrons are shared in a structural formula. So if I give you these molecular formulas and their corresponding structural formulas, how would you draw the Lewis dot structure? So since there are 4 hydrogens and 2 carbons, you know the 2 carbons are going to be in the middle. So I'm going to put the 2 carbons like that. And then I will put the 4 hydrogens on either side of each carbon like this. And then you will draw circles to indicate carbon has 8 electrons here and the other carbon has 8 electrons. Then you put 4 ovals around the hydrogens to showcase their 2 valence electrons like this. And voila, you have your Lewis dot structure for this molecule. And I'm going to shade the electrons that are in hybrid orbitals in green only in this one, so that you have an idea of how that looks like. Now, all the other electrons of carbon and carbon atoms are not in hybrid orbitals. These are just the valence shell electrons, the outermost ones. Let's do the next one, this one. So you have 1 carbon and 2 carbons, and then here's oxygen. Here are the hydrogens, and here are the 8 electrons of carbon, 8 electrons of the other carbon, and the 8 of oxygen, and the hydrogen electrons. And if you have CH3F, which is methane with the hydrogen replaced with the fluorine, you have 2 pairs of non-bonding electrons here. You show it like that. And make sure you mark these are called non-bonding electron pairs. When we look at 3-dimensional structure, they will become important. So if you are in group 6, you have 2 pairs, and group 7 has 3 pairs of non-bonding electrons. So let's look at the saturated and unsaturated fat structure. So all of these are molecules with 10 carbon in the carbon chain. And remember I told you most of the foods, everything organic is made out of covalent bonds. All the food you eat are also containing covalent bonds. So saturated fats, they are called saturated because they have all of the carbons are filled or saturated with hydrogens. These are generally unhealthy for you, and they are solid at room temperature, whereas the good unsaturated fats in a healthy diet like fatty fish, nuts and green leafy vegetables have carbon-carbon bonds with double bonds here and there. The more double bonds you have, the healthier the fat is, and they remain liquid at room temperature. The reason they're heart healthy is because of the kink. They are bent because of the double bond. It prevents them from stacking on top of each other in your arteries and creating clogs. These will stack on top of each other and make a nice thick structure or a clot, a place where your blood will clot. So anyway, going back to chemistry, let's look at dissociation energy of covalent bonds. So you don't have to memorize this. I'm showing you these just for understanding. So if it's a carbon-carbon single bond, the dissociation energy in kilojoules per mole is 348. It almost doubles when you have a double bond, and it increases a lot more when you have a triple bond. Here's an oxygen-oxygen single bond versus an oxygen-oxygen double bond. It's much higher, more than twice as high. And let's look at H2, hydrogen-hydrogen is bond length is this much, and here's the bond energy. And if you have hydrogen married to a very electronegative fluorine atom, look what happens to the bond energy. It goes up high. This is what I meant by highly electronegative elements bonding with you will create you having a higher dissociation energy. And here's HO bond for water, and NH3N and H for ammonia, and methane gas CH4CH bond is not very electronegative, as you can see, and the bond energy is much less. So the take-home point is the energy of food we consume is stored in covalent bonds between atoms. During digestion, food is chemically degraded by dissociating the covalent bonds within. Calories found in food describe the energy released when breaking down or dissociating all covalent bonds. Bond dissociation energy increases for bonds with higher electronegativity difference and more electron pairs shared. Just a little preview of things we have seen and will see. Bond length is the distance between the nuclei of two bonded atoms, and you measure it in picometer. Bond angle, we will look at it later, is the angles of any two bonds around a central atom due to electron repulsions in the valence shell electron pair repulsion theory. Bond energy is the dissociation energy required to break a bond. It's measured in kilojoules per mole. So let's look at VSEPR theory. So VSEPR stands for valence shell electron pair repulsion theory. It explains the molecular geometry of molecules. So let's look at water, H2O. You might think it's a linear molecule. It has those two non-bonding electrons on oxygen. They push each other because they're all negatively charged. They're like, get away from me. Their repulsion causes this bond to twist this way, forming a bent structure like this. And the the unpaired electrons are pushed apart like this, forming 1, 2, 3, 4 sides, like a tetrahedral, like this shape. Although there aren't any atoms on here, the lone pairs of electrons are spread apart like there were two more atoms around the central oxygen. This leads to a three-dimensional geometry called tetrahedral shape. So basically, VSEPR tells you that repulsion between valence shell electron pairs that are negative cause molecular shapes to change, bend, so that valence electron pairs can stay as far apart as possible. So let's look at some common geometries. If you have two areas of electron density, you're going to be linear. And if you have three areas of electron density around the central atom, you're going to be trigonal planar. If you have 4 areas of electron density around the single atom like this, you're going to be tetrahedral or trigonal pyramidal. If you have 5 areas around the central atom, you're going to be trigonal bipyramidal. If you have 6 areas around the central atom, you are going to be octahedral. We will look at this in some more detail in the next one. So here's your number of electron dense areas. And here are the molecular geometries, the angles between these bonds. This is 180 and this one is a 120. This one is 109. This one, angles depend. Some are 90 and some are 120. This one, each one is a 90. So the molecular geometry depends on whether you have lone pair of electrons or not. If you have no lone pairs, you are 180 degrees here. You can be trigonal planar or bent like this. If you have 4 regions of electron density around you, you can be tetrahedral. And if one of them is one pair of lone electrons, you'll be trigonal pyramidal. If you have 2 pairs of lone electrons, you will be a bent tetrahedral shape. There are other shapes in here. They're not in our syllabus, so I didn't show them to you. You only have to know the trigonal bipyramidal with the 120 and 90 degree angles with 5 regions of density, and the octahedral with 8 regions of, 1, 2, 3, 4, 5, 6 regions of density around the central atom. So if I give you the chemical formula of a compound and ask you to find what type of molecular geometry you have, this is how you draw it. You write the central atom and then put the other 2 aside and see if there are, how many areas of electron density there are. For example, are there non-bonding electrons or not? So if there's no non-bonding electrons and you have 2 areas, it's going to be linear. If you have 3 areas of electron density and there are no non-bonding atoms, it's going to be trigonal planar. Otherwise, it would be trigonal bent. If you have 4 areas of electron density, it's going to be tetrahedral for water and methane. And then if you have 5 areas of electron density like PF5 or PCl5, it's going to be trigonal bipyramidal. And if you have 6 areas of electron density, it's going to be octahedral. Let's look at the conventions for naming covalent compounds. There's 4 rules to remember. So when you write, say I told you what is the compound name of the covalent compound formed by nitrogen and oxygen. Nitrogen will come first because you write the element whose name comes on the leftmost side of the periodic table first. So you start with nitrogen and then you state how many of each atom it's got. And then you end the last name of the compound with the second atom, its name ending with the "ide." And then you use prefixes to say how many are there. So here are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. You do not use mono for the first element ever. We just ignore it. You can use mono for the second one. So here as an example, this is dinitrogen. You start with the prefix tetraoxide, dinitrogen tetraoxide. This is, we don't say mono. This is carbon dioxide. This one is carbon monoxide. You have to differentiate the two. And then this one is nitrogen, dinitrogen monoxide. This is carbon tetrachloride. This one is also called nitrous oxide in another naming scheme. Finally, let's look at the properties of covalent versus ionic compounds so that you can understand what they are. So at room temperature, covalent compounds are gases or they're liquids, and they have low melting points. They're low melting point solids. And ionic bonds are, compounds with ionic bonds are crystalline solids. They make crystals like salt and table salt and magnesium chloride and things like that. Their polarity is very low. Ionic bonds, it's very high. Solubility, dissolving in how they dissolve in what type of substance. Few are soluble in water. Many are soluble in organic compounds. Ionic substances, many are soluble in water, not soluble in organic liquids. So we talked about how these are formed. I'm not going to go over that. And then conductivity, they do not conduct electricity. Ionic compounds are excellent conductors of electricity when you dissolve them or melt them. The melting point of covalent compounds is low. Ionic compounds is very high. The boiling points are very low for covalent compounds and very high for ionic compounds. So if you put salt in pasta water, for example, before you start boiling the water, you'll have to boil it a lot longer to get the water to boil than because salt is an ionic compound. And then examples are methane and hydrochloric acid for covalent compounds, and sodium chloride and sulfuric acid for ionic compounds. They occur between nonmetals, nonmetal and a metalloid, and the ionic compounds occur between one metal and one nonmetal. Look at the summary. Covalent bonds are formed between two nonmetals, sharing electrons to become like the noble gas that comes after them. And they can be polar or non-polar based on the electronegativity difference. All molecules are made out of covalent bonds, and we looked at how to draw Lewis dot structures of covalent molecules. The shared electrons in covalent bonds go into hybrid orbitals, which both atoms have access to. Based on the number of electron pairs shared, it can be single, double, or triple. Bond length and is affected by the number of electron pairs shared. Triple bonds have the highest the lowest bond length, and single bonds have the highest bond length. Bond dissociation energy is the energy required for a breakup between two bonds. It increases when you have 3 electron pairs shared and less when it's 1. Or the electronegativity difference is high, then it's got a high dissociation energy. The dissociation energy of a bond is the same as the energy required to create the bond. And then based on valence shell electron pair repulsion theory, based on the number of electron dense areas around the atom, you get different types of molecular geometries and bond angles. Naming binary, covalent, and compounds is based on the number of atoms of each element present by using prefixes. And that's it. Please do the exit ticket. Thank you.